Hello, this is question 5 from the Step 3 paper in 2022. Got lots of integration going on here, so this probably would have been a fairly popular question when people were sitting it, I would have thought. People tend to like a bit of calculus. Let's see how that pans out though. So for part 1, we've got to show that integral, so this is 1 over 1 plus e to the x from minus a to a is equal to a for all a is greater than equal to 0. Okay, so if we're integrating something, I mean, e to the x stuff does tend to lend itself to substitutions, because if you just do a u equals e to the x, then you're going to end up with a du over u is dx, so it drops in quite nicely. But I do like the fact that this isn't a million miles away from just a straight natural log solution. So if I can get something e to the x related on the numerator, then all will be good. So let's go with that. I'm going to I can't multiply top and bottom by e to the x because I'll have an e to the x plus e to the 2x on the denominator. So e to the minus x is going to be better for things, because then I'll have an e to the minus x plus 1. And then I'm straight into natural log territory. These sort of things come up quite a bit. You get used to seeing this stuff. So this is a negative natural log because I've got e to the minus x. Don't have to worry about any kind of modulus because it's all positive stuff anyway. So I'll have that from minus a to a. So the minus in front of the natural log is flipping the limits really. And then I'm going to have two of them. I'm going to have one natural log subtracted from another one. So I'm just going to end up with a fraction at the end. So I'm going to have an e to the, so it's like putting the minus a in first and then taking off the a. So I'd have an e to the a plus 1 over e to the minus a plus 1. And that needs to be equal to a for all a is greater than equal to 0. I mean, this to me looks as though it's working for all a, doesn't it? I mean, but still, it'll still work in that case as well, unless I've missed something. But how am I going to get that equal to? So that's just equal to a, is it? So the contents of the bracket must be just equal to e to the a. So, well, let's split out, have a closer look at that denominator then. So 1 over e to the a, oh yeah, okay, yeah, fair enough. So that is a 1 plus natural log e to the a plus 1 over 1 plus e to the a, all divided by e to the a. So they're going to cancel, and I'm going to end up getting natural log e to the a, which equals a, which is what we want. And it's certainly going to work for a as being greater than or equal to 0, but it may well work for all values of a. So that's done part 1, which is a nice opener. Part 2, which looks like it's a bit more meaty. Explain why if g is a continuous function and that integral is 0, then g of x is 0. Right, so they're saying, so if we integrate g of x from 0 up to a, and we get 0 all the time, then g of x must, I mean, that's obviously true, isn't it? Because, so we're saying that if we've got some function, we're only going on positive x here, we're going from 0 up to a, and a is greater than or equal to 0. So if we start off, we've got to start at either a negative or a 0, or a positive or a 0. And then we increase our a, so we're either going to be adding a negative area, a positive area, or nothing. And we have to be adding nothing in order to keep on getting 0 for our integral. So it seems obviously true, but how am I going to put that into a convincing answer? Because I can't just leave this on here, a pair of axes and an arrow on it. Well, I'm starting from this base case, I suppose, aren't I, of saying, well, we've got to begin somewhere. A can be equal to 0, so let's go with that as a base case then. So the integral from 0 to 0 of g of x dx, I mean, that is just by definition going to be 0. But should I say that I don't know, how am I going to put this? Can I just write that is equal to 0, or is that going to be, do I want an intermediate step? I mean, I suppose I could say, let's put an intermediate step in and say, let f of x be equal to the integral of g of x dx. Do I want to have a plus c on the f of x because I've got an indefinite integral? Or do I have that as part of the f of x? I don't think it really matters, does it? I mean, I could say f of x has got that constant in it. So I don't think it really makes any difference. So in this case, then, that's going to be f of 0 minus f of 0, which equals 0, right? So I've got a foothold on something. So if I now do, so that's a bit separate, that statement I put there. Now let's do the integral from 0 to a of g of x dx. So that is going to be f of a minus f of 0. And that is also equal to 0. So I've got that f of a is equal to f of 0. Right, how does that help? Actually, this first bit doesn't seem to have contributed anything. I don't think that's adding very much. But if f of a is equal to f of 0, it means that it's just constant, isn't it? It doesn't matter what value of a we've got. We're just getting a horizontal line. So f of a, therefore f of a equals a constant, because f of 0 is a constant. Yeah, okay. So what? So f of a, well, we're dealing in x's really, so I could write that as a f of x is a constant. I mean, it's the same thing. Doesn't really make any difference which way I put it. And f of x is the integral of g of x. So yeah, so if I differentiate f of x, I get g of x, which is what I'm after. And f of x is a constant, right? Okay, so there we go. So therefore, d f of x by dx equals 0, and that equals g of x. And we've got for all x is greater than, oh, right, okay, yeah, fair enough. Right, so I haven't put these bits in here. So I need to, on this line, put for a is greater than or equal to 0, which means on this line, I need to put for x is greater than or equal to 0, which means I then need to put here that for x is greater than or equal to 0. Right, so that's made it a little bit messy, but yeah, I need to have this condition. I can't say f of a is a constant for all a. All I know based on this is that f of a is a constant for all positive a. So I need to have that included. Right, okay, so that was interesting. So now we've got let f be a continuous function. Oh, right, I've already used f, but anyway, we've got a new f. Let f be a continuous function f of x greater than or equal to 0 for all x. Show that that integral equals a for all a is greater than or equal to 0. Right, that integral's got great similarities to what we've just done up here in part 1. If and only if that thing holds, and hence if and only if that thing holds. Right, this is going to need a new sheet, isn't it? I'm not going to get all this on the bottom of this page. Right, so let's kick off here. So I've got to show that that thing holds. Right, we've got if and only ifs. So I need to have a completely reversible process here. I need to have whatever I get at the bottom is, I need to be able to work backwards again. So I need to be able to work backwards from here to here, because I can only get this result at the top if the thing at the bottom holds. So I must have this one-to-one chain going all the way top to bottom. Otherwise, I don't have an if and only if. So keep that in mind as we're going through it, I think is the idea. So I'm starting here with a minus a to a, 1 over 1 plus f of x dx, and that equals a, and that is for a is greater than or equal to 0. Right, so I need to get this in terms of what? I mean, we're bound to be using this thing because we've just done it in the same part of the question. And it does have something being equal to 0, but it does have different limits. That's going from 0 to a, but I've got some way of showing. Now, off of this first part, it seems quite useful, doesn't it? I'm saying some integral is equal to 0 if the thing that's being integrated is equal to 0. Now, all of a sudden here, I've got to show that this something is equal to 0, which isn't the integral. So I'm thinking if I can get this integral to have this inside it, then I can say, yeah, that's going to be equal to 0. But I need to change my limits. I need to go from 0 to a. So I need to say that is going from minus a to 0 of 1 over 1 plus f of x dx. Then go from 0 to a of 1 over 1 plus f of x dx. And that is equal to a. Okay. And I mean, the other thing of note in the result here is I've got these minus x's. So that's going to fit, hopefully, with flipping these limits around and getting a 0 to a on this one as well. So if I go with a minus x on this, that's going to be equal to then an a to 0 of a 1 over 1 plus f of minus x, but I'm also going to get a minus dx, and then I'm going to have the second bit, 1 plus f of x dx, and this is still, okay, I don't really need that a there. I'm thinking about the if and only if bit at the moment. I mean, I've definitely got actually, let's put the a back in, and then change these equals that I've got on the left here, on the left, because this is, I'm thinking about my reversible chain. That is definitely reversible from first line to second line, because all I've done is split that integral into 2 bits. And that is definitely reversible. So far I'm still on the if and only if train. So that is okay. And that is still equal to a. This minus dx is like flipping the limits. So I can get the first integral to 0 to a and then put it all under one integral. So again, that's going to be reversible. So I can double arrow it and do 0 to a. I'm going to have 1 over 1 plus f of minus x plus 1 over 1 plus f of x, all dx, equals a. Right, I've got a big chunk of the answer there. I have a big chunk. So I need to get a 0 on the right-hand side, which means I can then use this. And I need to get a minus 1 inside the integral in order to get the answer. So that a, yeah, and that's going to work, because if I integrate 1 from 0 to a, I get a. So that works fine, doesn't it? So I can now say that I've got the integral from 0 to a of 1 plus 1. Let's write it in the order that I've got it in the answer. So I'm just swapping over these two terms that are already in the integral, so that it looks exactly the same. I'm now taking off this a, so that's taking off the integral of 1 from 0 to a dx equals 0. And again, I'm double arrowing it. So I've got a if and only if on that. So now I can use from this. So therefore, from previous result, which is 1, I've got the contents of the integral is going to be equal to 0. Oops, I've written an equal, plus over 1 plus f of minus x minus 1 equals 0. But this is, because we've got the condition there, for x is greater than or equal to 0, because we've got that condition inside the previous result. Okay, so that was swell. And that would be reversible as well, wouldn't it? Because if that is equal to 0, then yeah, we're integrating some function which is always equal to 0. We're then integrating from 0 to a. Well, of course, it's going to come out as being 0. So again, we can double arrow, and we got if and only if all the way up. So that works. Then we need hence if and only if f of x times f of minus x equals 1. So that must be, I would have thought, I say must be, see this go wrong, but it seems highly likely that's just manipulating this equation. So if I multiply by both denominators, then I should be all right here. I'm going to have 1 plus f of minus x plus 1 plus f of x minus these two multiplied together. So that is going to be 1 plus f of x plus f of minus x plus f of x, f of minus x. Yeah, that's all of that is equal to 0, just about squeezing on. So what's cancelling? That's cancelling with that, that's cancelling with that, that's cancelling with that. So I've got 1 is equal to f of x, f of minus x. And again, these are all reversible. So I've got that all the way down. Right, that came out quite nicely. I actually had someone asking about this if and only if stuff the other day, because it sometimes feels as though, well, why wouldn't we have something that is reversible? But we quite often have things which aren't reversible. You know, even simple cases of where we're doing things like quadratics and looking at roots. Yeah, it's all well and good saying, oh, we've got a particular quadratic, so it's got these two roots. I'd say it did have two roots. So we've got some quadratic, ax squared plus bx plus c. There's our quadratic. It's got these two roots in this particular case. That's great. We can go that way. But you can't say, well, if we've got these two roots, we've necessarily got that quadratic. So that's what we're trying to show on this, that we haven't, with an if and only if, it's saying that we're getting a particular result. And the only way we can get this result is by having this particular condition. So it is very much a one-to-one chain going from top to bottom, which means we can then retrace our steps. We can be completely reversible. Yeah, there's no other way of getting this result at the top. You know, we can't have that this integral is equal to a if we don't have this. You know, it is both so both having this set up, what we've shown here at the bottom, not only causes this, but we can't get this any other way. So it's an if and only if, you know, so that's why we have to have this one-to-one chain. We haven't got some other chain which is feeding into our initial statement. It's the only way of getting there. So it has to be completely reversible. So yeah, you just want to take care on each step, and you think, okay, well, if I have gone from, you know, my opening statement here to this statement here, well, say I'd started here, does it necessarily take me back to the previous statement? Well, in this case, it obviously does. You know, and that's what we're trying to interrogate each step as we go through this process. Anyway, so that's dealt with part 2, and let's get a new sheet up for part 3. Let f be a continuous function such that for all x, f of x is greater than or equal to 0, and f of x times f of minus x is equal to 1. Right, so all of the conditions that we needed for this previous part of the question. Show that if h is a continuous function with h of x equals h of minus x for all x, then this thing is going to hold. Right, so this does look as though we're going to be splitting things out again, doesn't it? It does look as though we're going to be doing that, because again we've got the minus a lower limit, which, you know, causes us problems in everything that we've shown. So we're going to have to do that, I would imagine. So let's say then the integral from minus a to a, h of x over 1 plus f of x dx is going to be then from minus a to 0, h of x 1 plus f of x dx, and then from 0 to a, oops, I'll not put the brackets around that one, h of x over 1 plus f of x dx. So the same old thing. Then I'm going to be doing the old minus x and then flipping it thing. So this is going to end up being the integral from 0 to a of h of minus x over 1 plus f of minus x plus h of x over 1 plus f of x dx, some brackets. So, and I need to make that into just h of x. Right, so what have we got? Well, h of x is the same as h is minus x, so they've told us that. And then, so I need all the rest of it to just disappear. So that must be the result that we had for f of x, which, yes, it is. Because, yeah, 1 over, well, this bit of it, that's the bit that I've got. So that's equal to 1. So let's say, okay, since we've got h of x equals h of minus x, and result, well, let's call that one 2. I think I called one of them, I think I called this one 1 previously. So, and result 2, we can say this is equal to 0 to a of h of x dx. Right, so that was quite a friendly little interlude in the question. So it looks like part 4 might be all right. I might be able to squeeze that on here. So hence find the exact value of that. So we want to get it, I mean, they've gone hence. I mean, they haven't even done a hence or otherwise. So we are going straight off of that result. So I need to get this into that format and then show that my h of x and f of x meet all of these criteria that have been set up. And then I should be all right. So how am I going to do that then? Because at the moment I've got 3 different functions in there. I've got an e and a minus x, a cos x and a cosh x. I mean, cosh x is the one that seems sensible to get rid of. So let's turn that, let's look at that then. So if I've got e to the minus x over cosh x, let's not worry about cluttering things up with cos at the moment. So that equals e to the minus x, well, it'd be multiplied by the 2, and then I'll have an e to the x plus e to the minus x. Right, so that's going to be, I never like looking at it with a, right, e to the minus x on the numerator is bothering me, and it will make things so much easier if I write it like that, because then I can multiply everything through. And then I've got that, so that is going to be 2 over e to the 2x plus 1. Right, so that looks a lot more like this format, doesn't it? So now I've got, so therefore I've got the integral from minus pi over 2 to pi over 2 of e to the minus x cos x over cosh x dx is going to be the integral from minus pi over 2 to pi over 2 of 2 cos x over e to the 2x plus 1 dx. Okay, so I need to show that these things meet these criteria. So I've got h of x is going to be cos x. Actually, let's take that 2, put it there, just to make things a little bit clearer. So let's put inverted commas, h of x equals cos x. So I need that cos x to be equal to cos x and equal to cos of minus x. So cos x equals cos of minus x, that's true. So that is a big tick. I've got f of x is equal to e to the 2x. So I need f of x to be greater than or equal to 0, which is fine. I need f of x times f of minus x to be equal to 1, which also works. Okay. Oh, I need both of these to be continuous as well, don't I? So I also need cos x continuous. So that is fine, tick. F of x is continuous. So that is fine. So I've got continuous, continuous, greater than 0, multiply to minus 1, and have that symmetry. So yeah, so they've met all of the criteria, so that is fine. Therefore, I've got that this integral here, running out of space on the page, so let's just sort of cut over to this, is equal to 2 lots of the integral from 0 to pi over 2 of just h of x, which is cos x dx. So that's going to be sine x from 0 pi by 2. So that's going to be 1 minus 0 times 2 is 2. So that's come out quite a nice number. Okay, those last two parts were quite nice. I mean, overall, that was quite a nice question. I think people would probably be quite pleased that they'd picked that based on the, seeing all of this integration. The first part was fairly straightforward. Parts 1, 3, and 4 were, as step questions go, fairly straightforward. Even part 2 wasn't that bad. It's just stepping through, splitting up your integrals and making sure you're not doing anything daft with the algebra. So that came out overall as a fairly friendly question. No step question is easy, but that one dropped out nicely.